And this is my title, The Mystery of the Magnetotail. Okay, so, Mystery of the Magnetotail. Here is the illustration from our very first paper about the magnetotail. It was published by NSF co-authors in 1965, believe me or not. So my job today is to convince you, and probably myself, that after all this time, 5 decades plus, the magnetotail is still a big mystery. And I have 3 chapters in my mystery book. So, mystery of the thin current sheet, mystery of explosive activity onset, and the mystery of auroral substorm. But before I open my mystery book, I would like to thank a big group of people, some of them are here, who helped me with ideas and materials. First of all, I would like to thank all participants of the EC focus group, or EC team, led by Misha Sitnov. It was great time and burn, and we were very productive. This paper, Explosive Magnetotail Activity, is just published. It contains basically up-to-the-art state of magnetotail research. I also would like to thank focus group leads and co-leads who helped me with some materials for this presentation, and a group of my UCLA co-authors. With that, I will open the first chapter of my mystery book, this mystery of the thin current sheet. Okay, so if you open textbooks or do the exercise by yourself using Tsiganenko model, for example, you will find the typical thickness of the current sheet in the Earth magnetotail is about 1 to 3 Earth radii, and the current which supports this current sheet is basically diamagnetic, so perpendicular to local magnetic field by definition, and the current density rarely exceeds 1 nanoamp per square meter. To give you an idea what it is, it's less than 1 nanotesla per 1,000 kilometers. However, if you're curious enough and look through recent publication and recent empirical models, like one published recently by Grant Stevens, you will find that very thin and intensive current sheet appears in these models in the near-Earth sheet during growth phase of substorms. The thickness of this current sheet goes down to 1,000 kilometers, which is comparable to thermal ion gyro radius, and the current density goes up to 10 milliamp per square meter. So it's 1 order of magnitude larger than typical quiet or statistically average current sheet in the magnetotail. Well, these models are really great, but they do not explain you how the current sheet thinks. So do we know the process behind the current sheet thinning? The first answer is, of course we do. We all grown up with that, right? So first, we have reconnection at the magnetopause, reconnected flux tube. What did I wrong? Reconnected flux tube transported tailward, heads to tail. The flux through tail lobes, magnetic flux increases, current sheet thins up to some extent, and when it thins enough, something happens at this point, and boom, we have substorm. Very simple, right? No mystery, right? Wrong, I would tell you. Let's have a look to observations. And the ARTEMIS mission, we carefully planned. I would stress it's not just occasional configuration, Fortunate configuration of spacecraft. It was carefully planned. We have this configuration in the near Earth plasma sheet at around 11 RE down tail, with 3 spacecraft sitting roughly at the same Y GSM and separated along X and along Z GSM by roughly 2,000 kilometers. So it's comparable to, again, to ion gyro radius. And with this configuration, we can use 3-point chronometer technique and calculate one-dimensional current, so Y component of the current density. And here are data. I will briefly explain you what it is. I'm sorry, very busy plot. I'm world heavy champions producing busy plots. The first panel shows the BX component from all 3 ARTEMIS spacecraft. One of them is sitting in the northern hemisphere, the other one in southern hemisphere, and the third basically close to the equator, neutral. Second panel shows the Z component from all 3, and the third one calculated or estimated, by the say, current density. So what do we here? What do we see here? It's like about an hour plus worth of TEMIS data, and during these 50 minutes, we observed what we typically call growth phase, so thinning and stretching of the current sheet. You see that BX on this spacecraft, which are in periphery of plasma sheet, increases. Oops. I'll let it use. Increases BZ. This increase of BX indicates the thinning of the current sheet. BZ decreases, which indicates the stretching of the current sheet, and current density increases from about 5 nanoamp per square meter to roughly 20. Interesting point here, there are 2 fine gray lines, hope you see it, which shows below, calculated from pressure balance. And below doesn't change much, just few percent of change in below produced current density, order of magnitude increase in current density. And it's typical situation. Here I show statistical analysis made by Anton Artemiev. We calculated the big deal of these current sheets, and in all of them, rate of change of the low field strength is incomparable to a rate of change in current density. So just a few percent of below changes and order of magnitude increase in the current density. Another very interesting thing here is that when current sheet stretches, so BZ decreases, the current sheet the current sheet becomes shorter. So here is the plot showing the reversed scale, reversed length of the current sheet versus BZ. So BZ decreases, and the length of the current sheet decreases too. So current sheet becomes thinner and shorter. So we believe that what we observe here is the formation of a local deep, local minimum of the BZ in the near-Earth plasma shape. And in this situation, just shown here, there is a very localized thin current sheet, in the near-Earth plasma sheet, somewhere around 11, 12 RE down tail. This localized thinning and localized VZ minimum was predicted by some models. And all of these observations are inconsistent with the simple flux flux loading cartoon which I showed in my previous slide. So what's going on here? The clue or some ideas came from MHD models by, I'm not sure how to pronounce this name, but Antonios, Otto, and co-authors. These are results from the MHD models, but I like this cartoon which Antonios kindly provided. It summarizes two processes here. So first is this classical loading of the flux to the load because of reconnection on day side. But there is another process which they discover. It is the flux evacuation from the near-Earth plasma sheet. So here is the flux evacuation, and this flux evacuation produces this deep minimum in BZ and increase of current, here is the BZ minimum, and increase in current density, very localized increase in current density in the near-Earth plasma sheet. Okay, it's MHD framework. What can we learn about particle kinetics of this process? So here again, about 50 minutes of ARTEMIS observations. It's from two papers, ARTEMIS 16 and ARTEMIS 17. And during these 50 minutes, you see gradual decrease in BZ, indicating stretching of the current sheet, and increase in the current density. And here, the green curve shows the current calculated using 3-point kilometer technique. And the red one shows proxy to particle current, proxy to electron current calculated using this equation. So it's essentially it's curvature drift current, which highly depends on electron thermal anisotropy. So this is the anisotropy, and this is the Firehose stability criteria. And this plot below shows the electron distribution function, so phase space density versus logarithm of energy for these 50 minutes during current sheet thinning. And here I highlighted the region of phase space density with maximized electron anisotropy. And it corresponds to 100 to 500 eV electrons. Subthermal electrons are responsible for this current sheet thinning. Their current carrier and their anisotropy basically balances the stretch, the curvature force in this thin current sheets which form in the near-Earth plasma sheet. Interesting point here I would like to make. These electrons likely came from the ionosphere. Well, another interesting point here, these current sheets, electron-dominated current sheets, are not neutral. They are polarized, negatively charged. And this negative charge of the current sheet was predicted first, according to my knowledge, by Hesse and co-authors in 1998. And more recently, this negative charging of the current sheet appears in global hybrid simulations by Auroral group. So here is this results from their simulation. So the question is, do we observe this negative charge current sheets? The answer is yes, we do. I remember a paper by John Weigand showing that recently San Lu statistically studied current shift observed by MMS mission and found this electric field which changes sign. It's Z component of electric field converging to thin current shift, and it changes sign from northern to southern hemisphere, and the amplitude of this magnitude of this current shift is around 1 millivolt per meter, which is very close to what was suggested by models. So what about lunar orbit? We have our ARTEMIS probes at lunar orbit. Do we observe thin current shifts there? And the answer is yes, we do. And they are very interesting. These are a couple of plots from a recent paper by Stephen Shu, who is our helper, I guess, today. And what he found, these are two examples of thin current shift thinning. The magnetic field components are plotted in the variance frame. So maximum variance, intermediate variance in green, and minimum variance in red. So the most interesting and very unexpected results here is this bell-shaped maximum of intermediate component. This component of magnetic field is along the current. So this bell-shaped BM component maximizes at the center of the current shift. It's essentially field-aligned or respond to field-aligned current. And here our reconstruction of the data, or fitting of the data to this model. We use basically the force-free model to fit the data and reconstruction of the current. And yes, we observe very thin and very intensive current shift. So it's like 1,000 kilometers thin, which is comparable again to ion gyro radius. The current density grows up to 10 nanoampere per square meter, and this current is essentially B-parallel. I wouldn't tell field-aligned, but it's B-parallel. It is very unexpected result, and we still don't know what's the kinetic of this current shift, how they form, and why they are stable. The force-free current shifts are indeed stable, but we observe non-zero, small but non-zero, non-vanishing normal component of the magnetic field here. It totally destroyed the force-free stable current shifts. Interesting piece of information, this current shift were observed in the situation when thermal pressure in the plasma sheet was small. So essentially that means that thermal pressure is not enough to balance the magnetic field, and the magnetic field starts to evolve into force-free configuration. So we don't know nature of these current shifts yet, and we don't know their stability. Well, with this I complete my first chapter, the mystery of the thin current shifts. These are basically my conclusion from that. I showed that current shift thinning is non-uniform process along the tail. There are two processes, adding of the magnetic field to lock and magnetic flux evacuation from the near tail, which forms this localized minimum of Z and maximum in the current density. I would stress that Magnetotail current shift thinning is global scale kinetic process. And anisotropy of particles plays the key role in stability of these current shifts. current sheets, very thin current sheets are observed as far as lunar orbit in the tail, and we still don't know how they form. Here I pointed a few open questions in this field. So, first of all, I told you that current sheet becomes, what it becomes thinner, it also becomes shorter. And it really raises this question, how it may be stable. Stability of this current sheet is a big mystery. We don't know what is the kinetic nature of the current sheet observed at lunar orbit, and it's a great challenge to modelers. We need non-classical, non-Greb-Shafranov models to model these current sheets. Okay, now I proceed to second chapter of my mystery book, The Mystery of Explosive Activity Onset. And here I am coming back to these ARTEMIS observations. What we observed this minimum in BZ, in the near-Earth plasma sheet. We observe peak in the current density, but we do not observe reconnection there, or any instability. All these thinning during growth phases end up with earthward bursty bulk flow coming from somewhere down tail. So the question is, why? We stress our current sheet very thin. We minimize our BZ, no reconnection. So apparently it's not that simple. It's not enough to squeeze current sheet and minimize BZ to start reconnection. Something else needed. What? So first of all, where reconnection occurs, or maybe I should better say instability, occurs. There are several papers basically analyzing geotail, big deal of geotail data, stating that reconnection typically occurs at around 25 RE down tail. Cluster mission observed reconnection, or what identified by reconnection, in 32 reconnection events within about 200 tail passes, and cluster apogee was around 20 RE. So its reconnection happened between 20 and 15 RE down tail. Recently, we used ARTEMIS data and ions observed in ARTEMIS data by ARTEMIS within this reconnection outflows or reconnection ejecta captured at lunar orbit. And the temperature of ions and spectral properties allows us to pinpoint the birthplace of these ions. And we found that they originated at about 30 RE down tail, 25 to 30, not 15, not 10. So why? Why reconnection doesn't happen when in a point when current density maximizes and BZ minimizes? The idea came from big particle and cell simulations by Sitnov and co-authors, or first even from purely theoretical consideration by Sitnov and Schindler, who showed that unstable is not the thinnest current sheet here, but all of a sudden the hump, so local maximum in BZ, further down tail. It's looking very puzzling at the first place, but it was shown by big simulation made by different groups, and also MHD simulations, again made by different groups. And all of these simulations showed us that yes, indeed, this situation is unstable. So is it the solution? The first question is, did we ever observe this hump in the current shift. It's probably easy to say, but very difficult to do. They're almost hopeless to observe in situ observations. But statistically, we indeed do observe some, at least minimum, and something like hump in the BZ component. This is from Chao-Yu 2015. And blue curve shows the actual data. Yes, there is something resembling a hump, or at least minimum and local maximum there, but let's have a look. You see these huge error bars. So I would believe that probably this maximum is due to cumulative effect of burst about flows or dipolarizing flux bundle that would have stopped at that point. Another way to observe or to remotely sense the magnetotail configuration is to use low Earth orbiting spacecraft like NOAA Polarized. I would not go to details of technique how authors to do that. This is from Sergeyev et al. 2018. But their method, they basically use loss cone filling. So if BZ is small enough, ions filling loss cone. When BZ it became large, loss cone became empty. So they showed this situation, and their interpretation is shown here. They indeed, well, they infer from their observations that indeed this hump exists during growth phase of Substorm. So the answer is yeah. So question is, did we observe the BZ hump? And answer is yes, sort of. This hump again appears in empirical models, which I pointed before. This is from Stevens et al. 2019. So you see, these are profiles of BZ observed during growth phases of substorms. And indeed, we see this hump configuration. However, we do see it in this substorm, but not on that substorm. So it's probably not the answer, but it's suggestive that this situation may happen in the plasma sheet, and this configuration, as it was shown, unstable and may lead to explosive onset in the magnetotail. So my conclusions from this chapter, apparently it's not enough to squeeze current sheet to very thin sheet and maximize current density, minimize BZ component to start reconnection. Reconnection in the magnetotail is not that easy to start. We observed, it was shown in the simulation that configuration with BZ hump is unstable and may be a solution for the situation. So still we don't know how this hump forms. It's a big puzzle and a big mystery. Okay, so now I'm leaving my comfortable zone and step to very shaky ground of auroral observations. And you see I'm wearing this t-shirt for purpose, hoping that it will help me. All right, so I showed you some processes in the magnetotail. Typically we believe that ionosphere is sort of a TV screen, and we see magnetotail processes in this auroral TV. So what do we see? This is the plot showing a variety of auroral forms observed in the ionosphere. It's provided by Toshi Nishimura. So what do we see here? We see polar cup flow of plasma observed by radars. We see pre-existing auroral arc, so it stays there hours before onset. And we see streamers, first polar boundary intensifications, and so-called streamers, these narrow north-south auroral arcs, which often forms before onset, but not any time. By onset, here I use definition from Nishimura et al. So it's brightening of the equatorial boundary of the auroral oval. It's again kind of how to define onset is still very debatable question. This is another part of auroral observations. This is from Kepka et al. 2009. We showed totally different picture. We showed this patch of auroral brightening before substorm onset. Here is onset arc, and he claims that this patch came directly from reconnection, and when it hits the pre-existing arc, substorm onset happens. So first of all, yes, we see it on, in auroral observations, but what their counterpart in the plasma sheet? Often these streamers are interpreted as better say, low entropy plasma channels in the plasma sheet. But it's worth to remember that streamers and auroral patches and everything basically correspond not to flows or plasma motion in the Magnetotail, but field line currents that's generated by this flow. And the streamers, as it was shown by Rumi Nakamura, basically created by field line currents which are sitting on the westward edge of the flow, created by flow shear. And just to add another puzzle here, very recently Mayashita and Ieda reconsider published streamer triggered substorm events and found that auroral streamers and related process not responsible for the initial brightening. Initial brightening happened in the other places. Streamers hit the auroral arc there, but brightening onset happens there. So according to their analysis, these are unrelated events. Well, you see, we have variety. We have zoo of auroral forms. We may discuss these images for hours, but what we need is some sort of quantitative measure, how to quantify all these events. Some attempts were recently done in this field, and here I show a couple of plots from Kyle Murphy and others. So what they did, they track auroral brightness using the all-sky cameras and calculated the velocity of their propagation. It's very, very difficult to do. So we have different cameras. All camera has its own threshold, its own orientation, its own noise level, and so on. They took this everything in account, and calculated the velocity of auroral forms during growth phases of substorms and expansion phases. Here, if you see this dashed red line, it is threshold of background convection. And this plot tells me that during growth phase, auroral arcs, the motion of auroral arcs is basically below the background convection in the plasma sheet. The fast auroral forms are very rare during growth phase, but during expansion phase, situation is totally different. There are many of fast-moving auroral forms. Okay, another auroral form which recently found attract lots of attention is so-called auroral beading. It was found that pre-onset auroral arc starts to form vortices. So it's like shown here. It's from Matoba et al. 2012. And it happens minutes prior to onset. There were many papers showing observations of that and interpreting this beading as Rayleigh-Taylor type instability in the near-Earth plasma sheet. But mapping is a big issue here. I cannot buy this mapping what Matoba, the co-authors, showed in his paper, in their paper. Also, it is unknown and highly debatable, is this auroral beading has something to do with substorm, with onset instability? I think it's my personal point of view that it does not. We observe this beading often 10 minutes before onset in a different area with respect to onset arc. So, okay, this is a summary of my auroral mystery chapter. I wouldn't repeat all of them. I would just stress that mapping is really a unsolved issue. And unless we know mapping, we don't know how to interpret these auroral forms. And also, it's probably my personal point, many of you will disagree with me, it's a kind of a belief to think that the ionosphere is just a TV. We don't know what the relative roles of processes in ionosphere, auroral acceleration regions in the Magnetotail in formation of the pre-onset and onset auroral forms. Okay, this is my last slide, and this question we ask ourselves often and ask again and again: what we need more to solve or at least address these mysteries? I don't really want this mystery to be solved during my life. So what do we need more? Data, models, or both? I think both. We definitely need some physics-based framework, which includes global scale electrodynamics, magnetohydrodynamics, and kinetic physics. As I showed, this current sheet thinning, for example, it's global scale processes, but it is kinetic process. We need kinetic models to address it. We also, what is really needed is data model assimilation. I don't like term assimilation. It's like Borgish a bit. But that's what we need to put our data into context. In terms of measurements, it's clear to us now that the region, the transition region between tail and dipole magnetosphere is critical to understand how energy flows from magnetotail to the inner magnetosphere and to ionosphere in this region, this transition region, the energy of bursty bulk flows, all these transients is integrated and converted to field-aligned currents and others. So what we need is multi-point measurements in this region. We have three THEMIS spacecraft there, but it's not enough apparently. Another two types of observations which I would like to stress is, first of all, remote sensing from low orbiting spacecraft, like I showed example, which uses POSE spacecraft. But NOAA is about to stop POSE mission. So we need a fleet of spacecraft on polar, LEO polar orbits. Currently we have our own, I can't resist to stress it, our own UCLA Elfin Star CubeSats there, which are able to do these measurements, but we need to maintain a fleet of this spacecraft there. And another type of measurements which are very interesting and highly underutilized are the global imaging of the plasma sheet. Here is an example of that using TWINS ENA instrument. It's by Kesey et al. 2011. This map shows the temperature distribution, ion temperature distribution in the plasma sheet. It's very interesting measurements, and that allows us to see kind of 2D map of temperature distribution. And then these measurements are highly underutilized, as I told. Okay, I guess I'll stop at that point, and thank you for your attention.
Thank you, Andrei, for this wonderful mystery book. I hope this will enjoy for young people for the next decade to try to solve this mystery. How much time?